So if you have followed along from the last video, this video would probably make more sense, and if you haven't, then well, I won't really go into the details of what each of these things are doing, but the goal here is to build a classifier, more specifically a binary classifier, and we will be using the logistic regression model here. And needless to say, this is not production ready software that we are building. This is just like a toy function that we will be building so that we can actually get our head, we can wrap our head around what this whole thing is about. Let's say programming, this is going to be part 0, where we just get the data. So let's call it getting our data. Okay, so sklearn has this neat API where you can just call the load iris function, like object, which has a bunch of things. So of these things, we just need the data part, which would be the features, which would be the actual inputs, and we need targets. And these are the these things are related to the descriptions of what we have inside our bunch object. So just to get an idea of what features we are dealing with, we can just print. So let me just change this. Let me call it Iris. Would that be a problem? No, it won't. I guess that way we won't get confused that easily. So now it should be iris.data.shape. Makes more sense. So essentially we have 150 samples, each with 4 features. So let's explore the features. Let's explore the first sample. So what does this mean? This means that in this first sample of the iris dataset, we have the sepal length equal to 5.1, sepal width 3.5, petal length 1.4, and petal width 0.2. And which flower is it? Well, for that we need to check out the target variable, and we're talking about the index 0. So we have this 0. Now I don't know what 0 means, so iris dot, let's say, target names. Yep. So this means that 0 means it's the Setosa species, and if we had 1, it would be versicolor, and likewise for 2 it would be magenica. Again, let me just remind you that what we will be building is a binary classifier. So now we do the important task of actually turning this problem into a binary classification problem. So let's start using some variables here. Number of samples, or conventionally it's the small m. So let's just keep it at 100, and we don't need anything else here for now. Now let's prepare the dataset, prepare custom dataset for this, for the purposes of demonstrating the model. So what we'll do is we'll just extract. Actually, we don't need this. What we'll do is we'll take x, let's just call this x again, and we'll take only we need the first 100 rows, right? And we need all the columns. So let's just do this. So this will extract the first 100 rows, custom, and return counts, we set this to true. So now you can see that we have 50 cases where it's Iris Setosa and 50 when it's not. So ideally this does not happen. You have the distribution isn't this symmetric, but for demonstration purposes it should work. First we need something that will give us a sum, this dot product, which is the weighted sum of tables, and the theta here is these are the weights, and if our function works then we should have weighted sum theta as an x. Oh, it's not returning anything, my bad. It has to return this, right? So how did we get this? Well, if you do 3 times 1 plus 2 times 2, you get 3 plus 4, which is 7. Yeah, so that makes sense. That's correct. Simple function. What we need to do is we just need to return this value 1 plus np dot x minus x. For a very large value it should be close to 1, and for small positive values it should be close to 0 actually, and some bad variable names value. So you can see that I'll just print the large value here so that it's, you can see this, and similarly here we can say small value. So you can see that for 10, which is a large value, we're tending to 1, and for 2 we have 0.8. And further, yeah, so this is correct. Yeah, so this is what you should expect. This, we run a loop, we iterate through the entire training set, or usually it's on a batch, but this is a very simplistic example, so we're doing this over the entire training set. And for each and every instance we do these things. X is your input vectors, y is the target labels, -1 this, which is this outside term, and this internal term is the summation, which is simply the cost. So if all goes well, we should have one number, which was essentially the goal here. Give us one number and tell us how bad the model is. So let's just run this on some inputs and see what happens. That's this. Okay, we got this as a matrix. We got two values here. Why did we get two values? And let's do xi dot shape. Yeah, that's the problem. Okay, so we actually needed two-dimensional inputs. My bad, I didn't notice it. So this should be the case actually. So this means that we have a two-dimensional input where the first two values are this. Okay, now it's 2 2. Now you see you get the perfect result here. You get one number, S0. Since we just have one instance, it's 0, right? So the true label is 0, but this weighted sum. Now let me just interpret this for you. What this means is, according to our logistic regression model, that for this particular instance, the probability that this instance or sample belongs to the positive class is 73%. Let me just put it that way only. Percentage probability that this belongs to the positive class. But we know from the true label that this is actually an instance of the negative class. So a good cost function should give us a very high value for this. So now let's check the cost here. Okay, so you can see the value for this cost is, let me just remove these things, we don't need them. Now value here is 1.313. okay, to contrast this with another example, I'll just copy all this. The only change I'll make is, in this example, I will change the true label to 1. So this means this should give you a good probability for this, a higher than 50% probability, which is a good sign. Let's check this again. See, there's the difference. Here the cost is really less. Now what do I mean? So let's add another one here where we have the same example. Okay, let's have 2 and -1 or 10, let's say. So in this case the sigmoid will be higher, right? Because there's 2 and 10 here, and if you do the weighted sum, it would be 10, and the sigmoid of 10 would be very close to 1. So that means it is predicting it's a positive instance, but in our output labels it's 0, which means it should be a negative instance. So let's check the weighted sums. Let's just check the cost directly in this case, because I won't run through the whole thing again. Let me just check the cost real quick for this one. Right, so this is the cost. Okay, now if I change this thing here, where now this is a positive example, so cost should decrease, and it decreased obviously because both these are predicting positive instances. They are predicting that these instances belong to the positive class. So that means the cost function works. So we will probably need a vectorized implementation for it. Let's see. Let's copy this. Where is the gradient? This is the gradient. Okay. gradient. There we go. So the difference about the gradient is that the gradient will be for each and every theta, which means in this case we were returning a real number, which is a cost. That's the whole point of a cost function, that you give me all this and I'll give you a real number which will let you assess how good or bad your function is, your model is. But the gradient is essentially for each and every theta, so means each and every parameter. So this should give you +1, and I'll get into why this is n+1, but for now let's just see what we have. Yeah, so it returns a vector, and where each entry theta, let's just call it I, is the gradient of the ith parameter, right? So theta 0 would correspond to this delta j theta 0, delta j of theta divided by theta 0 subscript 0. So that's what it means. So now that we know what we are computing, let's compute it. Here x0, this 0 is the I, the superscript, and if I do this, here, so this x0, this entire vector, is our x superscript I, and this is subscript. This one is subscript. We can check for that. For the first gradient, for the first entry of this gradient vector to be filled, this becomes 1. So let me just rewrite this again, this part. So this should work. Yeah, that's it. So essentially this is your sum of the differences between the sigmoid of the weighted sum and the output divided by m, which is simple to compute, right? So we have the grads of I, which in this particular instance is simply grads of 0 to 1 by m into the depths, which was simply the sum here. And for the other cases where it's not as simple, what we do is this would be used again. So I'll just take this part, right? Okay, so here again we do the same, but in this case let's just mention that this happens when we don't need this. In this case we need to incorporate this part. Now this essentially means that we are multiplying each and every one of these differences that we get with the jth feature. So what that would mean is, for in this case, let's say if we have a vector like so 4, okay, and we needed to calculate gradient of theta, say 3. Now in this case we will be considering for this part the third feature, which in this case would be 3. So whatever we get after this difference, let's just call it diff here, we multiply it with this 3, right? So this expression essentially, this is what it means. So let's change this accordingly. So we do the sigmoid of the weighted sum, that's okay, and then we subtract it. Up till here it's the same, I guess. Yeah, this part is identical. Now this multiplication thing is new. Here's the new thing. Now we take this difference that we had here and we multiply it by the jth feature. What does that mean? It means that for this particular sample, the jth feature, but in this bad notation that I used, it's actually I, what we have. Let's make a random example here again, just to test this out. Okay, so for the thetas, let's keep this simple, -1 and 1. So this essentially means theta 0 is minus 1, and theta 1 is 1, theta 0. Okay, the x is here. So in the original problem for this one, oops, this one that we are talking about here, in the original problem here, we would have just one feature per sample, right? So that means that this can be anything like all right, the way I indexed it is wrong, or maybe it's not. Maybe it's not. Let me just this thing here, the addition of 1, I am already doing it, so that's why the dimensionality here becomes 2, right? So we have two rows here, but this is assuming that the vector that we give it does not have this additional 1 added to it, which is why it's doing this n+1 thing, which is why when you loop through this part, there's a problem, because the I that we use here, where is it, this is essentially this same 1, so we just change this to 1. So the important thing here is the inputs, let's just should have the extra feature theta 0 equal to 1 added to it, not theta 0, sorry, x 0. Okay, so let's print the cost, print the gradients. There it is. So you can see that cost is one number as we expected, and gradients are, how do you interpret this? The gradient for theta 0 is this and theta 1 is this. Now we have all the tools that we need to write the final learning algorithm, which uses gradient descent. And just to be clear, we are using what we call batch gradient descent, I think, which means it essentially goes through all the examples for this step. To get the theta, it's going to go through all the examples. There are other variants where you don't have to do that. We are using batch gradient descent. And another thing is no regularization. We're not using any of that fancy stuff here. Okay, so let's write the code. This is the final thing that we'll be using to mention this algorithm itself. The main algorithm. We start with random thetas. Okay, this is a very bad guess that we start with. Then we compute the cost. Then we compute the gradients, which tell us they will help us reduce the cost. Compute gradients. Then we tweak the parameters. This is the step which is important, where every theta I is essentially becomes, this means assignment step, theta I becomes theta I minus the learning rate into the gradient of that particular theta, right? And yeah, so keep doing that until if okay, satisfied with cost, stop, else go to 2. This is roughly what we'll be doing, right? Okay, so let's do the final training here. So or we could do that, or we could just pre-decide how many iterations we need. Either way, let's see what happens. Sorry, yeah, m by 1 matrix of 1s, and we'll add that to x, and this is our new x. Okay, now for the n, which is used to denote the number of features, now we'll simply keep it as x dot shape 1, which is columns of x, right? Because we have already added the 1 here. Okay, what else? So let's begin. Yeah, we need to initialize thetas. So thetas has to have the same dimensionality as the n here. So yeah, let's just do np.random.random. If I remember this correctly, this should give you, yeah, correct, n. Okay, now let's begin. So first, what do we do? First we compute the cost. So let's say let's compute the cost, which comes from gradient function, which again has three arguments, theta's, x and y, and the m argument is again constant. So I'll just pass this m as the m. Cost also had an m. Okay, so now that we have these things, we will do the updation step here. So this is step 4, right? Updating thetas. So now what we do is we can actually do it as thetas equal to thetas, no, equal to thetas minus the alpha into gradients. Now what I essentially did here is I'm subtracting alpha times gradient for each and every value inside the theta vector. So to give you an example of what I did here, let's just say that these were the thetas, okay, and let's say the gradients were this 0, 1, 2. Gradients here were -1, 2, 3. Okay, the learning rate, which is alpha, was 0.1. So what I did was I did thetas test minus learning rate into gradients. So you can see what happens, right? We have a new set of thetas. We went from 0, 1, 2, and to test it out, you can just see we are doing 0 minus -1 times 0.1, which is simply positive 0.1, which is what we have. This will update the thetas. Now check cost again. Check cost again. Cost again. Actually, this cost isn't needed. Actually, we don't need this here. Check the cost, which is j. These are the new thetas, and x, y, m. Let's print the cost. Let's print the iteration number as well. I iteration number. Let's put it as iteration. Cost is the cost, right? That should do it. And yeah, and then m is 100. Yeah, it's 100, and the others are okay. What did we do here? Alpha into grade. Oh, that's a bad mistake. I forgot to call the gradient function. I just left it as a function object. Okay, thetas x, y, and m. Okay, let's do this. Okay, so that was quick. And then we go here. So how low can the cost get? Let's see. 100 iterations. Okay, so the cost does decrease. It would be better if I just put all this in a graph, and the y is the cost. A range. Okay, so you can clearly see that we start with the cost around here, and then it decreases with the number of iterations. Now let's do something with the thetas now, because the whole point of this exercise was to build the model, right? So let's see. So let's just create a dictionary for this. Lookup target name. Okay, and let's just do this. Okay, so for I in this, k should be I, and we should be actually let's enumerate on this. For I val this, let's see what we have here. That's it. This is what we wanted. Why? Well, the actual value we'll get from this. So you can clearly see that this does not belong to Iris Setosa class, which is why the probability is only 10% that it belongs to Iris Setosa class. Now let's take another example where, okay, now we have Iris Setosa. Here the probability is super high, it's 85.87%. This means that our model is confident enough that this is Iris Setosa itself. So you can keep playing around with it. Now to actually, we don't have any test set or validation set here, so we'll just do the accuracy thing on the training set. Okay, so for the accuracy we would need the predictions first. Accuracy score. Now let's call this accuracy score on the y true, which is y custom, and the predictions. Okay, so we have overfitted really well. This doesn't usually happen. Yeah, but the point is that we did build an entire classifier, and this was expected to overfit because of the number of examples that we have. Let me just recapitulate what we did. We first got our data, then we implemented these functions, the building blocks or the ingredients, and then finally we had a loop which was the training algorithm, which was this entire thing. And this is actually what we needed. This whole thing, this whole procedure that we did was so that we could have the thetas. And then we tested out some random examples to see how good or bad our model was, and turns out it was pretty good. It was so good that it was overfitting. But yeah, so that's the end of this. I hope you enjoyed. If you did, like this video. Thank you.